Hi, I'm Kelly Beck, and I'm going to go over my problems for this project turn-in. So my first one is a cooling Gatorade. So it's a Gatorade bottle that's hot in a car, and you're cooling it down in ice water. So I've given the ambient temperature of the car, which you assume to be the temperature of the Gatorade bottle starting out. So I've given all these knowns and the heat transfer coefficient, the dimensions of the bottle, and I tell everyone to assume that the temperature of the drink is always uniform, and so are the coefficients provided. So how long will it take to cool down to 50 degrees Fahrenheit? So the drink properties can be assumed to be approximately that of water, and solve using lumped analysis. Determine if this is appropriate, radiation is negligible, and I've also provided all of these other values here. So I definitely edited this problem a lot. I've edited all mine, and so I added a bunch of things into the problem statement to make it more clear what was going on, and I also added the figure to make it to be able to imagine the problem a little bit better. Going down here, the learning outcomes are conduction, transient heat transfer, 0D due to lumped analysis, and it's cylindrical. So here, once again, are the knowns, the find, the time, and my assumptions restated again. The properties, and all the equations I will use for the problem. So the main two equations are the Biot number, which we did find to be lower than 0.1, therefore lumped was applicable for this problem. And then this here equation here, which is what we then will use to find time, which I found to be 8.79 minutes. This is my second problem. So it's a spherical tank with a Star Wars liquid inside it. So I did find sources, but I based off of the values that I needed off of coolant. So this, I've given the uniform temperature of the tank. So basically there's a coolant tank containing it, but we want to avoid condensation because that tank is kept at a really low temperature for the travel purposes. So we are trying to find what gap we need to put between the tank with the coolant and then the covering of it to avoid that condensation. So I've given all the dimensions and temperatures and dew point temperature, and mentioned like due to condensation we need a gap between a cover and the tank containing the liquid. So it's a concentric outer cover on the tank with a gap, and I've given the natural convection heat transfer coefficient, the emissivity, and all these different values. I also put our assumption to the radiation exchange between the outer and the surroundings is negligible, and I want everyone to calculate the gap size in order to keep the outer cover temperature above the dew point. So here's a little image. So I definitely expanded upon the problem based off of the feedback. So I added some more details, and then a little image because I know this question's kind of out there. The learning outcomes, convection and radiation. It's spherical and convective heat transfer, natural convection, and condensation. So here are the knowns, finds, assumes again, then the properties, some equations that I used, the convection term, and yeah, all that, and then L gap right there. And essentially from there, you just use all those equations and plug and chug and solve until you can find R2. And my R2 right here is this value, and then I found L gap. So that's essentially that problem. Hi, so this is my third problem. It's a dragon cooling, so like a carcass cooling. So I've given a ton of different dimensions and temperatures and like at the time of his death. I've given the velocity of the winds and the temperature of the winds that are cooling him down. And all my sources are listed here. I did use sources for a Komodo dragon instead of like an actual dragon because like that's the closest I could do. So I've given those dimensions, which those dimensions are true to what I found online for like what a dragon would be, like a size approximately. So I'm asking how long it'll take to cool the center temperature of the body down to 0 degrees Celsius, and I'm asking if this time is reasonable. So disregard any heat transfer from the bottom and the top. So here's some useful information down here. and an image. So I also say to approximate it as a cylinder. So here are the learning outcomes: conduction, transient heat transfer, 1D, and it's cylindrical. So this problem I adjusted based off of my feedback, gave an image, and I kind of specified more in my problem statement and adjusted my learning outcomes to it as well. So here are the knowns again, finding the time. And originally I had like any parts will freeze, but I decided to scrap that since it didn't really add anything to the problem. So my assumptions again, my properties, and all the equations. So the Biot number is important, and then this is the term for one term approximation with tau. And this equation was what I was going to use for if it freezes, but I again decided to scrap it, but I left it in here just to see how I adjusted everything. So from there, you just plug everything in and use table 4.2 to find your values. And I did interpolate as well. So after plugging everything in, I found that it took 3,926 hours to cool down, which is not a reasonable number, which makes sense because this is kind of dragon cooling. So yeah. This is my last problem for this turn-in. It's a curling iron. So I've given the diameter, and it has a coating around the inside of the material. So the coating is titanium, and the inside is chromium. So I've given all those values that you'll need for the problem there. I've given these as well, which have sources, and I asked to determine T-center and T-interface. So I do tell everyone to derive and solve the conduction equations using boundary conditions so that there's not any confusion over the way to solve this, which was a recommendation, which I updated my problem on. I also tell everyone to assume the curling iron can be treated like a wire with a coating. And then I provided a picture as well, because that was also some feedback that I was given. And yeah, so then learning outcomes are conduction equations including boundary conditions, deriving and solving, and it's cylindrical. So here, down to my solution, I put my knowns again and my finds, and then I restate my assumptions while also adding steady state, 1D, constant K, and all uniform heat gen, and all the other assumptions that I stated in the problem. So the equations are listed there as well with the boundary conditions, and those are really important to the problem. And then solving it, you just integrate a couple times and use your boundary conditions to find your constants. And then you keep doing that until you find T inside. And so since we don't know T interface, we have to continue on with this equation here for the coding, since the previous ones were for the inside of the curling iron. So you repeat the process of integrating and solving using the boundary conditions until you get this expression for the coding. Now you look at like the interface, you use all these equations here, and essentially just try to solve and isolate the interface temperature, which you can see me doing here. So I then plugged everything in to find T interface, and then used this equation to find the temperature at the middle of the curling iron. So yeah.